Welcome to today's solution of a challenging matrix problem from JEE Advanced 2025. We're given a matrix P with entries 2, 0, 0 on the first row, 0, 2, 0 on the second row, and 0, 0, 3 on the third row. We need to find the number of 3x3 invertible matrices Q with integer entries that satisfy two crucial conditions. First, Q inverse equals Q transpose, making Q an orthogonal matrix. And second, PQ equals QP, meaning Q commutes with P. The straightforward approach would be to represent Q as a general 3x3 matrix with 9 unknown entries, A, B, C in the first row, D, E, F in the second row, and G, H, K in the third row. If we directly compute both PQ and QP and equate their entries, we'd get a system of 9 equations in 9 unknowns. However, this approach is quite complex and error-prone. Instead, let's use a smarter approach based on commutativity properties. Here's a fundamental rule about matrix commutativity. If a matrix Q commutes with both matrices A and B, then Q also commutes with A plus B or A minus B. This follows directly from the distributive property of matrix multiplication. We can write Q times A plus B equals QA plus QB, which equals AQ plus BQ, which equals A plus B times Q. This simple rule will help us decompose our problem into simpler parts. Now, let's cleverly decompose matrix P. We can write P as A plus B, where A is the matrix with 2, 0, 0 in the first row, 0, 2, 0 in the second row, and 0, 0, 3 in the third row. Notice that A equals 2 times the identity matrix I3. Matrix B is the matrix with all zeros except for a 1 in the bottom right corner. Here's the key insight. Every matrix commutes with the identity matrix and therefore with any scalar multiple of it, like 2i3. So Q automatically commutes with A. This means we only need to ensure that Q commutes with B. Let's compute QB and BQ explicitly. When we multiply our general matrix Q by B, we get a matrix with zeros in the first 2 columns and CFK in the third column. When we multiply B by Q, we get a matrix with zeros in the first 2 rows and GHK in the third row. For these two products to be equal, we need the corresponding entries to match. This gives us C equals 0, F equals 0, G equals 0, and H equals 0. This is a significant simplification. With the commutativity constraint applied, our matrix Q now has a much simpler form. It becomes a block diagonal matrix with entries AB in the first row, DE in the second row, and zeros in the third column of the first 2 rows, and zeros in the first 2 entries of the third row with K in the bottom right corner. This block structure will make our calculations much more manageable. Now we apply the second condition. Q inverse equals Q transpose. This is equivalent to saying Q times Q transpose equals the identity matrix. The ijth entry of Q times Q transpose is the dot product of the ith row and jth row of Q. When we compute this product using our simplified matrix Q, we get a matrix where the top left 2x2 block contains A squared plus B squared, AD plus BE in the first row, and AD plus BE, D squared plus E squared in the second row, with K squared in the bottom right corner. For this to equal the identity matrix, we need specific conditions. From the orthogonal condition, we obtain a system of 4 equations. First, A squared plus B squared equals 1. Second, D squared plus E squared equals 1. Third, K squared equals 1. And finally, the off-diagonal constraint, AD plus BE equals 0. These are the only equations we need to solve, which is much simpler than the original 9-equation system we would have faced with the direct approach. Now let's count the integer solutions carefully. The equation a squared plus b squared equals 1 has exactly 4 integer solutions: 1, 0, minus 1, 0, 0, 1, and minus 1, 0. Similarly, d squared plus e squared equals 1 has 4 integer solutions. The equation k squared equals 1 has 2 solutions: k equals 1 and k equals minus 1. If these were independent, we'd have 4 times 4 times 2 equals 32 solutions. However, the constraint AD plus BE equals 0 is crucial and eliminates exactly half of these combinations. This constraint creates a dependency between the solutions of the first 2 equations. After accounting for the constraint that eliminates half the solutions, we get 32 divided by 2 equals 16 valid matrices Q. Therefore, the answer is 16, which corresponds to option C. This problem beautifully demonstrates how clever matrix decomposition and understanding commutativity properties can transform a seemingly complex problem into a manageable one. The key insight was recognizing that we could decompose P and use the fact that every matrix commutes with scalar multiples of the identity matrix.